everyone, my name is Steve Samuel from Design Visionaries, and today I'd like to go over the Phyllotaxis spiral. Also related is the golden rectangle, the golden ratio, and all of this cool mathematical stuff. And I thought, you know, people talk about it, not everybody seems to understand it that well, and so I thought I would just go into it, really go into it, and tell you what's going on. So I have this golden rectangle, and basically what it is I start off with a rectangle. In this case, the length of this side is 500 millimeters, and I'm going to make sure that this side is the golden rectangle ratio. Now I've got the number memorized. It's 1.61803, 1.86, 1.618034. Is that what I typed in? 1.618034. And oh yeah, and I've got to multiply that by the 500. There we go. So it's a long long way around it, but now I've got a rectangle of the golden ratio. And what's so special about this golden ratio? Well, everybody's seen these cool spiral patterns that you can make if you take a spline and you put it on the end points of the golden rectangle. This little doodad. And the thing is, you can keep going with this spline into infinity. And there we go. I just click on all the different points and say OK. And we've got this very familiar spline. Let's do a tangent here, from there to there, doink, and etc. So everybody's seen this thing drawn. You know, people use it when they shouldn't. I think I missed the point here. You know, people are always using this on the covers of books and so on and so forth, and people are always thinking of it as so special, and it really is. But mathematically, there's some amazing things that you can say about it. Okay, so there it is. It looks a little better now. So how do you derive this thing? Well, it's pretty easy, actually. So with the golden rectangle, what you do is you drop a 45-degree bisector so that you're basically making a square shape. So we do that. We make sure that's 45 degrees. 45, like that. And then we bisect the end of that one. So we bisect the rectangle at that location. So you have a square here, and you've got another, now you have another rectangle that is the exact same ratio as the first rectangle. So now we can do it again. You take a little line segment, you go at the end of that point, you're off by 45 degrees, you give it a trim, and now you're ready to do your next line. Your next line starts at the end point of this. You go to there, you trim that off, and you keep going. So this is a very simple process, like so. And I could do this into infinity. Just get smaller and smaller and smaller. But every time I make a new rectangle, this rectangle here, new rectangle, there. So now, this new rectangle, this one here, is the same ratio as that one there. It's the same ratio as that one there. So you just keeps going into infinity. And 1.618034, and it keeps going, is the only number that will do that. So cool. So now we also have a relationship in a circle. and we have an angle in a circle. So here's an angle, and here is a slice of this pie, and we have a specific angle that relates to the golden rectangle, and that angle is 137.5. Now, where do I get that? Do tell. So here's the math that goes along with the golden rectangle. If we let the distance from here to here be 1, then that's the small side of the rectangle, and the large side of the rectangle is x. That's the number we're looking for. And then since these two rectangles are the same, we get the length of this side of the big rectangle is 1 plus x. We got this as x, obviously, because it's a square. So we have 1 over x equals x over 1 plus x. So it's just the ratio of this side to this side equals the ratio of this side to that side. Makes all the sense in the world. So then we cross multiply. X times x is x squared. 1 times 1 plus x is 1 plus x. So we've got x squared equals 1 plus x. And then if we get everything on the left side of the equation, we've got x squared minus x minus 1 equals 0. So now we have it set up like this. We can plug it into the quadratic equation. I had a wonderful math teacher whose name was Zelda Druce, and she would have us recite x equals negative b plus or minus the square root of b squared minus 4ac all over 2a. You've got to remember, all over 2a. She was a fantastic teacher, somebody who really, really cared, somebody who was, I think she was like 5'3", but she was a force to be reckoned with, and she gave me my love of math. Anyway, Samuel J. Tilden High School, graduating class 79. So, Zelda Druce said this quadratic equation, if you set this equation up, then the coefficient in front of the squared term is a, coefficient in front of the regular x term is b, and then you have c. So a equals 1, b equals negative 1, c equals negative 1. And when you plug it into this equation, you get 1.618034. So then, if you divide 360 degrees by 1.668034, you get about 222.5 degrees. And if you subtract that from 360 degrees, you get 137.5. So it turns out that this golden rectangle has its application for these spirals. So what I've created now is a piece of geometry where I'm rotating a circle, and I'm making it bigger, and I'm pushing it outward every 135 degrees, 137.5 degrees. So that is how I make this thing happen. Here's what it looks like. And now, here's how I did it. I'm going to do it from scratch. And in order to proceed, I'm going to create a sketch. And I'm going to put a point location right there. And I'm going to fix that point with a fixed command. So let's go into settings and do fixed. And we'll pop in a fixed point. So that point is now fixed. And now I'm going to make a length of line. And I'm going to put a circle on that line. There we go. The circle is going to be a certain diameter. And the length of the line is going to be a certain diameter. And I'm going to start the festivities off with a length of 4. And a circle diameter of 4. Just like that. So I'm starting small. And then I wanted to put an angle actually on here. So I'm going to get rid of, oops, I'm going to get rid of the vertical constraint on this. Remove all dimensions, remove all constraints. Okay. And what I want to do is, I'll just try to get rid of this doodad. Delete. Okay, there we go. And I'm going to push this over here. Okay? All right, good. Now, this dimension that I have here, as you can see, it's not a parallel dimension. It needs to be parallel. So I'm going to delete that. I'm going to put a reference line here. And I'm going to put a dimension here. This is a parallel dimension of 4. Now, I want to give names to these dimensions because I'm going to use them again. And this is going to be A1. That's my angle. A1. And this is going to be L1. L1. It's very nice that you can name your dimensions in the sketch. And this is going to be D1. D1. Okay? And I'm going to start A1 off at 0. So it's top dead center. So there you have it. I have a little circle. I have a line that pushes the circle over. I have an angle that I can change. Let's do that. Make sure it's working. Okay. And I don't need this anymore, so I'm just going to make that a reference. Cool. So now I have a piece of geometry that I can pattern. I can increment the pattern. I can increment the angle, which I'm going to be incrementing it by 137.5. And I'm going to increment the length of that line, and I'm going to increment the diameter of the circle until I get what I want. So cool. So now I've got this little piece of geometry, right? Little lie in there. What's next is creating some expressions. So that A1, I'm going to have an increment. So that's an A1 INC. The angle increment is going to be 137.5, just like we calculated. That's going to be the angle, the increment that I'm going to add to the angle. So that's A1 INC. L1 INC is going to be 2 inches, or 2 millimeters, or whatever it is. And then D1 INC, the increment on the diameter, is going to be 2 also. Great. And then I'm going to do an NN, that's the number of holes that I want, or the number of circles. That is going to be a constant number, so my dimensionality is unitless. And let's start NN off as 20. All right, so cool. So now we have something to do. We have in the Home tab, we have the pattern feature. And this pattern is going to be a very sophisticated pattern, so we want to make sure that this says variational rather than simple. You don't do variational, it doesn't work. And we're going to do a patterning of this sketch, a circular pattern, and we're going to specify a vector, and the vector is going to be the one that sticks straight up out of the page. I'm going to just rotate like this. It's going to be that vector, and we're going to rotate about this little point right here. Boink. Okay, great. Now the count that we're going to have is NN. So we're going to have NN of these things. And the pitch angle is going to be 0. Now that might be kind of confusing. The pitch angle 0, so all of them are going to end up in the same exact place. Yes, they are, except we have this beautiful pattern increment here. Pattern increment. So now we use our increments that we created in the expressions list. The first thing we're going to do is increment the angle, and the angle is going to be incremented by 137.5. That's a given. Enter. And then we're going to pattern the length dimension. I'm going to double click on that, and I'm going to type in L1 INC. That's the increment. And hit enter. So we're patterning the distance that the circle is away from this little point. And finally, we're incrementing the diameter. So we have diameter, and we have D1 INC. And we say OK. So this is odd. We're doing a rotational pattern with a pitch angle of 0 with a count of NN. So theoretically, they should all land right on top of each other, except we're doing an angular increment to the actual sketch by 135. So there we go. So now we have a awesome pattern, but the circles are running into each other, and I don't like that. So I've got to make the circles bigger, or I've got to make the increment on the length larger. So the L1 INC I can change right here. I'm going to make it 4. And as you can see, it's now better behaved. And I'm going to experiment here. I'm going to make it 3.5 instead. So that's nicer. It looks like it's getting real close here. So I'm going to change the increment on the diameter. And that was D1 INC. So I'm going to make it 1.5, let's say. Cool. And now I want to see many more of these. So n equals 20 right now, and that's trivial. So I'm going to put 300. And NX is going to go. My computer's going to warm up. Woo! And it's sitting there calculating. It's showing me the instances here. It's up to 280, 290, and 300. Look at that. Woo! That is awesome. Could you imagine trying to do that manually? It would be impossible. So now you can see that the circles are running into each other. So that means the increment that I had on the diameter was too great. So I'm going to go to D1 INC, and I'm going to make the increment 0.75, let's say. And then the whole thing's going to recalculate. You can see the progress down here. It's up to 140, 190, 200, and we get to 300, and that looks better. So as you can see with these little increments, you can make these changes and get this phyllotaxic spiral. The math is very simple as long as you remember your algebra. Remember Zelda Juice. I remember her. I will always remember her. She taught deep into her 80s, as I was told, and what a fantastic person who touched the lives of so very many people. Teachers are heroes. Let's always remember that. You know, they don't always get paid very well, and they sit there and they give us a future. So this little talk is dedicated to Zelda Juice and Marty Malamed, who is my physics teacher, Mrs. Marks, who is my biology teacher, Marty Pasternak, who taught me history, Sheldon Spielberg, who was my swim coach, all in Samuel J. Tilden High School. And I had a yoga teacher whose name I don't remember, who was also fantastic. The phyllotaxic spiral is amazing because it's the same thing that when you look at plants growing, when you look at succulents, when you look at leaves or buds coming out of a plant, it follows this pattern. So nature knows about 137.5 degrees, or 1.618034. Isn't that amazing? So I love math. So I was going to stop the video just by showing you how to do the phyllotaxic spiral with just the pattern feature, but then I thought, well, it would be really great if I could show you how to do it with the algorithmic modeling, nodes. And so I began to do that, and I realized that the video is way too long. So, so what I'm going to do is I'm going to make another video with the phyllotaxic spiral done with the nodes, as you can see, done with the algorithmic modeling, and I'll show you all the details. So thank you very much for, this is kind of a long video. Thanks for hanging in there with all the different things I've done. Please like and subscribe if you can. Help us out on the channel. Really appreciate it. We're approaching, I think we're over 5,000 subscribers now. I'm really proud of that. And, you know, through it all, our whole idea is to be folks who serve the public, give, you know, like teachers do, and really appreciate the fact that people watch this and give me such great feedback. So thank you very much. See you soon. I think the next video will be more of the algorithmic approach to this. NX is incredibly powerful. You can do these things with spreadsheets. You can do these things with just the pattern increment. You can do it with algorithmic modeling. You have always a choice with NX, and that's one of the reasons why I love it so much, and it makes it so powerful. So thanks again. I'll see you soon.